Good evening, 316ers. This is the second part of our mini lecture series talking about distributions and why do we care about them. So I'm calling this one So What? We're going to talk about the importance of distributions in statistical inference and really concretely lay out why we care, why you have to trudge through all of this in order to figure out the properties of a distribution. What does it get you? And then we're going to also introduce two different types of distributions, the binomial distribution and the Poisson distribution, and the circumstances when we would use those. So just to review the big picture that we had gone over in the previous lecture, what we have typically when we are working with statistics is limited information. So that's starting right up here with the sample. Okay, so with our limited information, we can figure out our sample statistics, we can figure out the sampling variability, we can figure out the sampling distribution, which gives us measures of shape. So that's the symmetry or unsymmetry of the distribution, whether it's normally distributed or not, the spread, which depends on the sample size, and measures of center, which are the mean and median. And if we have decreased our bias and if we've decreased our variability, and remember we decrease bias by taking random samples and we decrease variability by taking lots of random samples, then our sample mean is going to be pretty close to the population mean, which is a key link here, okay? And that goes back to our discussion of the central limit theorem. So I'd also told you in the previous mini lecture that there were 10 specific propositions that you all need to become really familiar with, okay? And these propositions were specifically that samples are selected from populations, which is pretty easy. Populations or population distributions are described by parameters, which are the one true value of the population of mean or standard deviation or variance. These parameters, these true values, are actually constant in value. We assume that they do not change, that there is one true value. Samples, on the other hand, are described by statistics, and statistics are variable quantities. When we look at the distribution of sample statistics, so if we took a whole bunch of simple random samples and then took the mean of each of those simple random samples, we could construct a distribution of the sample means, and we would call that a sampling distribution. We know that the sampling distribution of the sample statistic is approximately normal, and I want you all to remember what we're saying here is it's approximately normal. It's not exactly normal, it's not normal, it's approximately normal, and we're going to come back to this in later slides. We note the sampling distribution of the sample statistic is characterized by shape, center, and spread, and we know that the spread of the sampling distribution is related to the sample size. So this is going back to the central limit theorem. When we have more observations or more samples in our sampling distribution, the variability is going to decrease, which means that our estimator, our sample mean, is going to be closer to the population mean, okay? And that's what this last one is. The sampling distribution is centered at the population parameter. That's all that means, is that the sampling mean is equal to the population mean. Okay, so basically what we're doing is we're taking a bunch of simple random samples from our population, and they will be truly random, and we are going to take a lot of them. So we're going to have a sample, and then from that sample we're going to make some inferences, or we're going to make some statements that we can support with evidence about our population. So that's pretty convincing, I think, for, why are we doing this? But let's make it even more concrete. Why do you really need to know this information about distributions, and particularly normal distributions, and the relationship between the sampling distribution and the population distribution? Well, in the whole point of statistics, and we're going to have a class specifically devoted to this, is to ask good questions, okay, to ask hypotheses. And so a hypothesis is a question that you're interested in answering, or you can think of it as a very specific way of asking a question using statistics. The point underlying hypotheses is that we are using limited data. We're using our sample data to answer a question about the entire population. Now, because we have limited information, we have limited data, we can't just say, the population mean is exactly this value, or, yes or no in response to the question. We have to acknowledge that we're working with limited data and to make some accommodations for that. But some questions that you might ask using your knowledge of distributions is, for example, do undergraduate students at UAlbany drink more than undergraduate students at every other university? Are women paid equivalent salaries to men, or do levels of PFOA in Central New York exceed the rest of the country? So how are we going to figure that out? Well, one of the ways is just looking at the normal curve and understanding the relationship between where an observation falls or where a sample falls within the curve. Is it 1 standard deviation? Is it 2 standard deviations? Is it 3? So what this graphic tells you is that if observations or if samples are within 1 standard deviation, it's pretty much considered the same as the mean. So if we took a simple random sample of UAlbany students, and this was the distribution of undergraduate drinking everywhere, and the UAlbany students were right within the first deviation, then we could actually say, as an answer to our question, well, no, UAlbany students drink about the same as other undergraduate students. Do women make more than men? So we could actually have our curve here, and we could look at men's salaries, where they fall within the mean, and where they fall in terms of deviations within the mean. And we can look at women's salaries, and we can say, well, no, they don't actually. Or if we're talking about levels of PFOA, we might see that levels in New York are way out here, way past that 3rd standard deviation, out in the territory of, there's definitely less PFOA, or there's definitely more PFOA in the water. So this helps us to answer questions where we have limited data. Okay, questions that are generalizable, that are based on this knowledge of the underlying distribution of the data. Okay. So examples of normally distributed statistics. So I'm going to bring you back to this point again. When we're talking about distributions here, we're talking about the distributions of statistics, the distributions of sample statistics. So normally distributed statistics are the mean, the variance, and the standard deviation. And, with just the mean and the standard deviation, you can find a normal distribution. So this is going back to our Excel work. So if you actually wanted to, you could type in, equals norm.dist, and you could have some value, and you want to see the probability of that value come up. So let's say a 1 with a mean of 9 and a standard deviation of 2. Okay, so that's going to give me a probability, a very small probability. Whoops. Here. And this is the probability that the value is less than 1. Okay. And we can see here that after subtracting it from 1 to get the value of 0 to 1, that it is very tiny. So what we have here are examples of normally distributed statistics, but unfortunately not everything is normal. Okay, and by this I mean that not everything fits into the normal setting, at least not at first. So remember, by normal, we're talking about this normal curve that is symmetric, It has very standard spread, right? When we standardize our normal curves using our formula for the z-score, we can set the mean at 0 and the standard deviations at 1. But not everything fits into that really easy setting. So sometimes we have to use our knowledge of other distributions in order to be able to answer those questions that we were talking about. So two of the different distributions we're going to talk about are the Poisson distribution and the binomial distribution. And the reason for this is because we have some non-normal statistics that we're really interested in using, okay? So some examples of non-normal statistics include probabilities. So what is the probability of an event occurring or not occurring? What is the probability of having a 0 or a 1 show up in your variable? That is an example of a probability. And then we also have counts. Okay, so you can think of counts like rates. So an example of a count would be how many cars I see driving through the stop sign in front of my house, right, every hour. Or how many children came by my house for Halloween every hour. Or how fast does a car drive over a distance of 80 miles. So these are things that we use to describe samples, right? And that can tell us really important things, but they don't fit into our understanding of a normal distribution, right? Because for probabilities, especially for probabilities in the binomial setting, we talk about only having values of 0 or 1. And for counts or rates, you're talking about things like 1, 2, 3, 4, 5, over an amount of time, which can be, it can't be represented as normal. So what we need to do is to be able to know the distributions of probabilities and counts to find out some things about them so that we can generate those distributions. And then what we're going to figure out, or I'm going to tell you now as a spoiler alert, both the Poisson and the binomial distributions approximate the normal, which means they come to resemble the normal when we have enough observations in them. So that's the big spoiler, surprise. But let's get into talking a little bit more about what the Poisson and what the binomial distributions actually are. So this is just a reminder that what we talked about before in terms of assumptions that you need to know, you should memorize these. The sampling distribution of the sample statistic is approximately normal. So we've talked about two sample statistics, counts and probabilities, that are not normal but will approximate normal, which is one of those important assumptions that we have here. Okay, so what are the binomial and the Poisson distributions? Well, the binomial probability distribution is used when we're talking about trials that have a probability of a success or a failure. So the key here is probability. We talk about having X number of successes over the total number of trials. Binomial probability distributions can be described using only N and P. Okay, and at this point, N is the number of trials, and P is the probability of success. So this is very similar. I want you to make the relationship here with normal distributions. We can describe them just using the mean and the standard deviation. Binomial probability distributions can be described using the number of trials and the probability of a success. When we have enough observations, the binomial looks like the normal. Okay, the Poisson distribution is used when there are events that have a small probability of occurring that happen within an interval of time or distance or space. What we're talking about here is a rate at which an event occurs. So for this, think about chocolate chips and a chocolate chip cookie, right? So you have one of those big mall cookies in front of you, and there are chocolate chips in there, but the probability when you have a bite that you're going to get all chocolate is actually very low. Okay, so you can count the number of chips per bite, but the probability of getting a ton of chips per bite is actually very, very low. So that is one example of a Poisson distribution. A key way to distinguish binomial probability versus Poisson is for binomial, we have a success and we have a failure, right? We have to have two specific outcomes that are happening, and they are disjoint, okay? Binomial probability distributions are disjoint and they are independent. Poisson distributions don't have to be disjoint. Okay, we're talking about counts and rates, so it's very different than what we know about the binomial probability. And the Poisson will also approximate the normal. It will also start to look like the normal as when there are enough observations. So I'm just going to take this and pop it down here. Okay, great. Okay, so some more stuff about Poisson and binomial distributions. Counts, which are again are the Poisson distribution, and probabilities, which are the binomial, are categorical variables. We're focusing here specifically on discrete random variables. And we're going to start off by talking about the binomial, which only has two possible outcomes, right? 0 or 1, yes or no, success or failure. There's a specific name for it. We call it a binomial variable. And for binomial variables, we use probability, or p hat, as the summary statistic. When we talk about binomial variables, all you have to know in order to calculate p hat is that it is the number of successes over the total number of observations. Okay, that's pretty easy. You guys have done that before. It's just the number of successes over the number of observations. The binomial setting, okay, so it's important for you all to think about in what circumstances you might use the binomial distribution. So if you hear probability, you should be thinking, ooh, binomial distribution. The binomial setting means that there is a fixed number of observations, so maybe we have 100 coin flips or 1,000 coin flips or, whatever. All of the observations are independent. There are only two possible outcomes, and the probability of success is the same for each observation. Okay. For the binomial distribution, there are a couple of things that you should know. We describe, as I said before, the binomial distribution using n and p. N is the number of observations or the number of trials that we have, and p is the probability that x, our discrete random variable, occurs. The distribution of x is b, n, and p, which just is describing the entire binomial distribution. Let's skip this. You guys don't need to know this. Okay. If you know that you have a binomial setting and the population is much larger than the sample, you don't need this. Okay, so we streamlined it. 3 things you need to know. Actually, 2 things you need to know. We described the binomial distribution using n and p. You should definitely know what n and p are. Therefore, we can describe the whole distribution of any random variable that is a binomial variable using the binomial distribution and our knowledge of n and p. Okay, so we're going to move on. Okay, so now we know what the binomial setting is, the circumstances in which we can use the binomial distribution. We need to know 2 other things. We need to know the binomial coefficient, and we need to know that in order to get the binomial probability. Now, the binomial probability is just the same thing as when we're calculating the probability of an event occurring under a normal distribution, right? When we're talking about using the normal distribution and the normal distribution function in Excel to find the probability of getting a 93 on a test or getting, between an 83 and a 93 on a test. Binomial probability will tell us the probability of getting a success or failure over a certain number of trials. So the first thing we need to know is, what is a binomial coefficient? It's just a way that we can arrange the successes that we have. So if we're flipping a coin, how many times we'll get a heads over the total number of observations, which is n. So that could be the total number of coin flips. The calculation for that is just, and don't get freaked out, this notation that says n over k. Okay, and that's just saying that we have a certain number of ways that we can get n observations over k successes. And the exclamation points that we see here, all those are a factorial language. And don't get freaked out, stay with me here. So the binomial coefficient, we know that n is the number of trials, we know k is the number of successes, and we know that the exclamation point indicates factorial notation. And all that means is that the k factorial or the n factorial is equal to the number times 1 minus the number times 2 minus the number times 3 minus the number until it gets down to 1. So if k was equal to 5, k factorial would be 5 times 4 times 3 times 2 times 1. Okay. So with that, if you are evaluating the occurrence of cancer in a population using a simple random sample of a population that has not been exposed to pollution or cancerous material, so there's no dependency here in the data, let's say that your sample size is 100 and you take 150 samples. The probability that a case has cancer is 0.08. So once again, your sample size is 100. You've taken 150 samples. And the probability that a case has cancer is 0.08. So what is n in this case? In this case, n is the 150 samples. It's 150. Okay, so what is k? Well, k would be 0.08 out of 100. So your sample size is 100. And the probability that a case in your sample size has cancer is 0.08. So that would just be 8. So in Excel, we can calculate the binomial coefficient using our formula, n choose k. So that's all this is saying. N choose k is equal to n factorial over k factorial times n minus k factorial. All right. So remember, our n is 150 samples, our k is 8. So n choose k. Let's go into our Excel here. So n is going to be 150 times 149 times 148 times 147 times 146 times 145. You guys get the point. But it's not always practical to sit here and type in all of those numbers. So what we use is a function in Excel called fact. And then we have an open paren, and the number we put in there is just our n. So we put equals fact 150. That returns a really large number, as you can imagine. Where this is an exponential notation, it's just telling us that the number is really, really big. So we can try to make it bigger here, and this is just telling us that we're going to go out 262 to the 262nd power. So what we need after that is to know what k factorial is, because our formula is n factorial over k factorial times n minus k factorial. So if k factorial is 8, we need to do equals factorial 8, remember, because that's 0.08 of the 100 that we have in each simple random sample that we're taking. So all we would do is to take those numbers and put it into a formula where our numerator is n factorial, and we're going to divide it by k factorial multiplied by n minus k factorial, or excuse me, n minus k. So n is 150, k is 8, and we're going to use the factorial notation here. Okay, and we're going to make sure that our denominator is in parens so that we can keep our order of operations. So we find that our binomial coefficient is quite large. Okay? Now, if I'd made this something a little bit easier, right? Like instead of 150, we had 15. And if k was still 8, we would see that our numbers here would change. Let's actually take it down from 15. Let's make it 5 to make this a little bit more tractable. So we can see we have a super large number here. And let's see if we can get this to show you. Okay. Well, it's equals 5 times 4 times 3 times 2 times 1. Okay, very, very large. And if we change that down here, okay, so I'm just going to change this back to what we had. So we had factorial of 150, and that's just, we'll make that a little bit smaller so that you can see it without all the hashtags in Excel. There we go. Okay, and I've done the same thing here. So that is how you would calculate the binomial coefficient, and really the only reason that you need to know about the binomial coefficient is because it's a really important part of the formula to calculate the binomial probability. Now again, don't freak out. This is a formula, and what I expect you to know if we were in a testing or homework situation is that you need the binomial coefficient to calculate the binomial probability. Okay, so what this formula is saying is that the probability that any discrete random variable is equal to the number of successes that we have, so it's equal to 0 or 1, is equal to our binomial coefficient times the probability using the number of successes in an exponent times 1 minus p, so that's just the complementary rule that we've used before with probability, to the n minus k. Now, I'm not going to ask you to calculate that by hand. What I'm going to do instead is to show you how you would figure that out using Excel. So you'll remember what we said was that in order to figure out what the binomial distribution is and in order to find the binomial probability, all you need is n and p. So n is the number of observations and p is the probability. So if your sample size is 150, you draw 150 samples of size 100, the probability that a case has cancer is 0.08. So what we would do is we'd go into an Excel. So let's figure out what is the probability that there are 10 cases of cancer. So we would calculate the binomial probability in Excel using the formula for binomial distribution, which is equals binom.dist, number of successes, number of trials, the probability, and if it's true. So in this case, what we would do is we would go into Excel and we would say, okay, this equals the binomial distribution. Okay, the number that we're looking for is 10 cases of cancer. We know that we have 150 trials, so 150 simple random samples. We know that the probability of cancer within the sample is 0.08, and we're going to type in true. And that gives us a probability that X is 1, that there is a case of cancer is 0.338427, or about 33.8%. So the probability that we would have 10 cases of cancer is about 33.8%. Okay, that's all we're saying here. Now this is a little bit different than when we're talking about a normal distribution and we're subtracting from 1, because in that case with our distribution we are looking at the number of cases between 0 and some number, and then we have to figure out where the interval or where the value we want is falling. For this, we're asking simply what is the probability of a success or failure. So this is going to tell us pretty directly that it is 0.33.8, that will have 10 cases. So, moving on. For binomial mean and standard deviation, what you should know is the binomial mean is equal to n times p. The standard deviation is the square root of n times p times 1 minus p. So if you have a probability of 0.08, this would be n, so let's say 150 times 0.08, and then you would just multiply it by 0.92, that's 1 minus p. So if we were going to calculate the mean from our cancer example, what we would do is we would take n, which equals 150, times p, which is 0.08, and that would be our binomial mean, which would be 12 cases. Okay, 12 cases of cancer. For the binomial standard deviation, what we would find is we would want the square root, okay, and we want the square root of n times p. So we have 150 times 0.08, and we would multiply that by 1 minus p. Okay, and I'm going to put this whole thing in an inclusive parens. Okay, and we find our standard deviation is 3.32 cases of cancer. Okay, so we know that we should expect an average of 12 cases of cancer. We know that the standard deviation is 3.32. So that's very useful for us. That puts everything into a similar language as with our normal distribution. All right. So basically what we're talking about here, and what I've said before, is when n gets large, when our sample size gets really large, the binomial random variable becomes approximately normal. This means that when we're talking about the sampling distribution of our binomial random variable, if we have enough, we can talk about the distribution in terms of its mean, which we've already calculated, and its standard deviation, which we also just calculated. So that's important information to have. So the next thing is talking about how you would calculate a Poisson probability from a Poisson distribution. And just remember here that Poisson distributions are used when we're evaluating the occurrence of a random variable over time, distance, or space. So we can talk about the amount of cars that run a stop sign. We can talk about the number of trick-or-treaters. We can talk about counts. We're not talking about probabilities where we know the number of successes over the total number. We're talking about counts over some distance or time or space. And that's the difference between Poisson and binomial. The Poisson setting, which you should know or you should become familiar with, is that the number of successes or the number of counts that we see in two non-overlapping units of measure are independent. The probability that a success will occur in a unit of measure is the same for all units of equal size and is proportional to the size of the unit. And the probability that more than one event occurs in a unit of measure is negligible for very small size units. All this means is that events occur one at a time. Okay? So when we're talking about the number of successes that occur in two non-overlapping units of measure, what we're talking about are units of time, space, or geography. So when we're talking about the number of successes that occur in two non-overlapping units of measure, we're just saying that the number of successes is not dependent, right? Having something happen in a mile or a minute or some time-space continuum is not going to affect the likelihood that it happens again in the next unit of measure. The probability that a success will occur in a unit of measure is the same for all units of equal size. Just means that, for example, if you're looking at the rate at which cars are going through the stop sign, that it's not any different. There's no difference in the amount of cars that are running the stop sign at 9 a.m. as compared to the amount of cars that are running the stop sign at 9 p.m. Okay? So that's what the Poisson setting is. And then just like with the binomial, we have this really scary formula where we have an exponent, and we have lots of Greek symbols, and we have factorials, and I don't want you to worry about that because the only thing that you need for the Poisson formula is to go into Excel and type in equals Poisson distribution, and that will say, okay, give me the count. So let's say we're talking about cars. I want to know the probability that I'm going to see 15 cars run through the stop sign in front of my house when I know the mean number of cars that usually runs through the stop sign per hour is about 7. And we're going to say that this is cumulative. So the probability that we see 15, or let's even make this even more clear for you all. Okay, so let's say that what I want to see is the probability that 15 will run through when 1 usually runs through per hour, and that gives me a probability of 1. Now what that means is that for this we actually need to subtract that 1 from 1, okay? Because looking at what I'm asking and what the mean actually is, we know that those two are not actually very likely. So we need to be subtracting the area under it, from 1, because this formula is returning the probability that the number of cars, the count of cars that are running through is anywhere between 0 and 15, right? And for this example, everything in my distribution is between 0 and 15. If I were to ask it something like, okay, what's the probability that I see 2 cars run through in an hour, it's going to give me a different probability. Okay, that's 91%. It's still very close to 1, but it's not exactly 1. So we would say the probability that we see 2 cars is about 8%. Okay? So I will see you all in class on Tuesday. I'm going to put up the homework assignment very shortly. You will have until next Friday to turn it in. And if you have any questions, please send me an email or bring your questions to office hours on Tuesday. Thanks and have a great night.